Will you put the screen? Yeah, as mentioned earlier, so we have David Humphrey from Germany. He is speaking from Germany. He is our Director of Research, ARC Advisory Group. David Humphrey is going to be speaking on future automation architectures, cloud, edge, virtualization, and MTP. So it'll be a great presentation. David, the stage is yours.
Okay, thanks. I just need to be made a presenter so I can share. Okay, here we go. I just need to.
Yeah, hope it's all right, David.
Yeah, it's coming.
Yeah.
That should do it.
Yeah.
Okay. Yeah. Good afternoon, everybody. My name is David Humphrey with ARC Advisory Group. I'm based in Germany, and I'm really happy to be here today to present live in our virtual forum. In 30 minutes, I want to cover a lot of material, so I'm going to get going right away. What I'm going to talk about is how we at ARC see automation architectures evolving due to primarily the strong influence of what I call commercial IT technology. I'll talk about how that's affecting what we call the industrial edge. And then I want to go over a few scenarios of how architectures could evolve, how they could look in the future. I'll give an example of how this is being done today at Audi here in Germany. And then I'll move a little bit into the process area and talk about modular type package, the MTP concept for modular architectures that is becoming more and more popular in the process industries. So what's driving things? Why are we changing things? It's really the gradual convergence or the ultimate merging, I would say, the inevitable merging of IT and OT. IT is obviously information technology. I call it commercial IT. That's the stuff they use in schools and in commercial companies, in banks and insurance companies. OT, I don't have it on the screen here, but OT is operational technology. I use it as a synonym for automation. OT sounds close to IT. It's very popular now. I still like calling things automation because that's what it really is. So we're seeing this influence, but what's happening is it's changing things in a slow state. Nothing ever happens fast in our industry. I think all of you will agree and nod your heads. Things take a long time to change. The reason is because we as manufacturers in discrete industries and in process industries, we have a huge amount of money tied up in the assets that we have purchased. And these assets, this equipment, this machinery is scaled to last for 10 years, 20 years, 30 years in operation. So nothing ever is going to change fast in a scenario like that. What we have seen for a few decades now is that that more and more applications and functions are becoming software-based. I'd like to say that there used to be no software. We used to really live in the industrial world in a purely hardware environment. Gradually, software crept in. At first, it was offline software for configuring a few devices, but more and more, especially in the last decade, we've seen software increase as the portion of a whole application. Hardware itself is becoming more and more standardized. Thank God, it's making it cheaper. And it's also starting to become a commodity, but we're really not quite there yet. Later on in the presentation, I'll talk more about virtualization, but what virtualization is doing is that's also another concept from the IT world that we're starting to see creep into our world. It has great advantages. It consolidates hardware and software, and it makes the hardware less important. And again, that means efficiencies and cost savings. Finally, I'll talk a little bit about what I'm talking about now is the industrial edge. The industrial edge is that space where automation systems, the way we know them from the past, are finally meeting IT systems and therefore being connected to the rest of the world. Let's take a closer look at the edge. ARC has a long definition of what the industrial edge really means. We've been developing it and modifying it for over 3 years now. I don't like the definition because it gets too technical. The edge is really just the space where IT meets OT. And if you see in the diagram here, the edge devices are actually the infrastructure, the gateways, the switches, the hardened, ruggedized industrial version of IT devices that you might use on the factory floor to add connectivity to your machinery. On the OT side, you have the classic side, the classic types of devices, endpoint devices like PLCs, sensors, actuators. PLCs have, and all types of controllers have been connected for 20 years. We've had an Ethernet port, but connectivity and the IoT go far beyond just having an Ethernet port. There has to be a lot more functionality present for a device to really be an IoT device. So let's take a look at the way we've laid out our machinery lines in the past and how we automated them. This is an example of a classic automation architecture from about 25 years ago. So what you see is a bunch of machinery connected. Each machine is delivered with its own PLC. Each machine has its own operator panel on it. The integration of the machinery is done after the machinery arrives at the end user site, and an integrator or the end user himself actually might go in and connect the PLCs, share some data. That PC that you see at the far left hand is what you might call a line PC. It might be running an application to maintain a database of collecting data from the PLCs, maybe managing recipes and sharing them over the network with the PLCs. The network itself, excuse me, is a network from 1995. By the color, I'm guessing it's probably Profibus. It's not Ethernet. It's not very fast. It's not really efficient for a large network. You also see some additional PCs that are connected along the line. Those would be PCs that are delivered by the machine builder with the equipment that add additional functionality that do things the PLC can't do. They might maintain a local database. They might provide visualization. They might do quality control right on the machinery. Again, equipment delivered with directly with the equipment. Now, if I advance 25 years, okay, maybe 15 or 20 or 25 years, whichever, but into the present day, this is what our architectures look like today. And I'm not sure if you were quick enough to catch that difference. I'm going to go back. This is about 25 years ago. Notice the color of the cable. And today, really, we've evolved only in the network technology. I'm making a bit of a joke here, but there's basically been very little progression in automation architectures in that time from 25 years ago. What has gotten better is the connectivity and the network technology. We now use Ethernet everywhere. This is an example. If it's green, it's probably Profinet, but it's not standard Ethernet because standard Ethernet wasn't good enough for our industry. We said for our purposes, we have to modify it, and we didn't do a good job of that. So today we have at least 6 different versions of what we call industrial Ethernet, but it's basically Ethernet, works like Ethernet, looks like Ethernet. What would happen if we, before I go to the next slide, just if you're an IT person, let's say your title is IT administrator, you look at a scenario like this. Again, remember the software installed on these local boxes on the machines. This is a nightmare for an IT person. The software is located and runs on machines that are in a dirty factory, maybe in a hazardous environment, and at all different locations and connected by networks that are non-standard. So maintaining this software is a nightmare. For the engineers, the mechanical engineers, the industry electricians, the automation engineers, this is normal. They don't really think about doing software updates, or for that matter, managing software. They never thought of things about things like maintaining a certain level of uptime, maintaining availability of software. These are all concepts from the IT world that were completely foreign to the world of manufacturing and automation. So back in the present day, we have our Ethernet cable. what if we took a bold step and took all that plant software? This is what I call level 2 and level 3 applications. This could be visualization. This could be some production management software, maybe some quality control, some specialty functions like measurement technology. What if we took that and consolidated it all on that device at the left-hand side? That would be, depending who you are, I might call it a plant server. Other people might call it a cloud. That's why the blue cloud outline around it. For those of you that are uncomfortable having software run elsewhere that's actually in the cloud, we can call it a plant cloud, which means it's on-premise. It's actually physically there, and it's being run and maintained by your own people. But nothing says that we couldn't have an outside company, a host company, actually host that software at a different location. Doesn't matter where. We have networks that are fast enough. We have the internet that's fast enough. We have reliability in our communications that that would allow that software to run elsewhere, and it might be run better. Maybe we could put the software in the hands of people who understand software, not the machine operators, not the plant managers, not the plant engineers, but people who really understand IT and know what to do with software like that. This is just a scenario for the future. I mentioned, it's not for the future, it's actually being done today, but I mentioned virtualization before. This would be done with virtualization. Virtualization takes software from different operating systems, sometimes even from different eras. This could be legacy software that has been around for 25 years and still has to run because there's nobody left to maintain it or to port it to a modern platform. So with virtualization, we create a container and put that software in the container and then let it run on that big server that's backed up and that has a high level of availability and reliability. And we allow people who understand software, people with titles like IT administrator, to take over the management and the updates of software like that. That would be a big step forward for our industry in allowing some of the practices that have been around for decades of the IT industry to be used in our industry and manufacturing as well. Now, this is almost heresy, but what if I went one step further and watched the PLCs, the little gray boxes on the green cable? What if we took those off of the machinery and off the line and consolidated those on the server as well? I've talked about this concept for a few years. I've actually had some companies requested that I don't talk about this in detail because it's going a little bit too far, but there are actually companies doing this today. If we have a good network, we don't have to have so many pieces of hardware out there on the machine running software. We can even consolidate the control software on a server and put it in the hands, put it in a safer environment for execution, and put it in the hands of people who understand the needs of that software and what has to be done. So if I go even one step further, this isn't a big step, but what if we modernize the network? The green cable is the green cable. As an example, might be Ethernet IP, it might be Profinet, but those are all what we call open proprietary networks. They're definitely not standard, and they all have one of the larger suppliers in the background pulling the strings. What if we moved our network to truly standard Ethernet? We can do that today. We can solve some of the speed problems just by using faster Ethernet. Gigabit Ethernet is becoming more popular in factories. We also have things like TSN. TSN is a timing mechanism that just recently, it's in the process of being implemented as part of standard Ethernet, which means it's available for everybody, and which means it'll be the only thing that you need to have for timing on Ethernet to achieve determinism. That's useful in applications like motion control, where you need very fast coordinated timing when you have several or dozens or even hundreds of axes that are coordinated. The second thing I mentioned is OPC UA. If I'm not going to talk long about that, but OPC is the OPC Foundation. UA is the Unified Architecture. This is many things, but it contains, among others, a set of protocols that are standardized that would, in the future, possibly replace the protocols in use by PLCs from their manufacturers. It's just it's a movement that's going on. It might take some time, but in the future we could stop worrying about the problem of the network by just using one network, just like the IT people have been doing since the early 1980s. We tend to focus a little bit too much on this color of the cable and that color of the cable. Wouldn't it be great if we just had one network to standardize? Talking about networks, all that wiring, what if we took another evolution step and did this? What if we got rid of the cable and replaced it with 5G? We just completed some research at ARC on 5G as used in industry. In this application, this is a plant with a limited size, a known size, a length and a width of the building and a height. Very soon, probably by 2022, you'll be able to install a private network in your plant using 5G technology, using incredibly fast speeds, much faster than we've ever been used to with wireless, with 4G, for example, which is used sometimes in the factory, but not very much, and certainly faster and more suited to the purpose than any form of wireless, even the new wireless 6 standard that's coming out. 5G is going to be a game changer, and it's going to provide that final boost of connectivity that will really drive our industry into the 21st century of the industrial Internet of Things. With 5G technology, all devices can be connected without a network cable, with more than adequate speed, with more than adequate bandwidth, and with the reliability that we need for industrial applications as well. That's coming soon, and that's going to obviously change the environment. So I like to call this sort of architecture an IT-like automation architecture, because it uses those concepts that I talked about, from modern standardized networking, software management, consolidation of software on hardware that's well backed up and made redundant 1 or 2 times over. The basic, well, just 3 that I mentioned here are, first and foremost, lower capital costs. If I use commercial technology, it tends to be lower priced. It's better known. You have a whole workforce with the skill sets to maintain it. It's much more efficient than using any sort of proprietary technology like we're used to in industry right now. Because it's better known, you have lower maintenance costs as well. So after you've acquired it, installed it, your total cost of ownership is going to go down, because your maintenance cost over time will be probably substantially lower. And for the cybersecurity freaks, I threw this in, it's a lot easier using modern standardized tools to implement cybersecurity. I mentioned one application. I was a bit surprised. For years, I've been talking about this as if it were future music. And then at the ARC forum that actually took place physically this year, in the beginning of February, it must have been one of the last events in the world that took place actually physically, where people came together before the onset of the coronavirus. But this one presentation was given by Dr. Henning Löser from Audi here in Germany, a car maker. And he talked about how Audi is standardizing on these units, for lack of a better word. He said basically they're moving from what they do now, which is if they need a certain function on the factory floor, then they buy a box. The box contains all of these devices. Obviously, there's a PLC in there. There's some edge infrastructure devices. He's got a firewall here. He's got actually 2 PCs doing something in there, and they're then talking to some sort of process device, which looks like a robot. In the future, he wants to move to from buying a box to buying a piece of software. In other words, somebody will provide the box and that'll be standardized. There won't be a PLC in it. There won't be all these individual boxes. There will be one PC-like piece of equipment, or he's got two here maybe, and all of the all of the functionality will run in software on these boxes. And his solutions will be a collection of these boxes connected to each other. The focus will be on software, like you see on the right, and not on hardware, like you see on the left, like it was in the past. Okay, I'm going to do a pivot in the remaining minutes I have, and I want to talk about modular production. In particular, there is this concept that we call modular type package that is growing in popularity, especially in the process industries. But going back to as far as I can remember, that's about 30 years. We've been talking about modular productions, about modular concepts for a long time. Sometimes we call it distributed automation, distributed control. It's all the same thing, really. I actually wrote on the right-hand side, you see a page from a report. I think I'll point out the date. I wrote this report in 2001. That's how old I am. And I discussed concepts of modularity and how PLCs can support that. And 19 years later, we haven't really come a long way because there haven't been good standards. What we've had is the typical network that you see, or this architecture you see on the left-hand side, that consists of a steep hierarchy from top to bottom, and a bunch of different networks. That's all the different cables you see in the different colors. This type of architecture actually hindered the development of true distribution of controller automation and slowed the progress towards modular production. The traditional approach, though, let's take an example of chemical production. It works pretty well here. The typical approach to designing a plant to produce a chemical is to build a pilot plant on a small scale and figure out the process, get all of the process parameters right. I mentioned a couple here, heating, mixing, reaction, cooling times, things like that. And once you have the pilot plant running, which is almost like a laboratory, then you scale up, you multiply everything times 100. You re-engineer it to produce that same product on a large scale, and it's probably more than factor 100. It might be factor 1,000 or 10,000. You can't just simply multiply by a single factor. You have to re-engineer everything, but you make everything larger, so it affects the design of equipment and the size, and affects all the parameters. This is the way we do it. This is the classic way to build a chemical plant today. The risk, obviously, is of overinvestment and overcapacity. Most plants operate in a range of between 60 and 120% of what we call nameplate capacity. And that means if demand shifts outside of this range, then the plant is likely to be still operating, but not in a very good way economically. In fact, during the crisis just about 12 years ago, a lot of world-scale plants that were the thing of the day, as far as like the latest to have, had to be closed, or production continued, but with a poor return on assets because they suddenly didn't need the capacity that was built in. So my question now is, we're in the middle of the COVID crisis right now. So what will happen today? Probably the same thing. Probably some plants will be, or already have been shuttered, or they're operating, but at not the capacity they need to actually make money for the owner operator. So the quick definition, or the quick explanation of the MTP standard, or the concept of MTP, is to not scale up like I talked about. In fact, I like this this saying here. It's you number up instead of scaling up. And what does that mean? Well, instead of building big pieces of equipment that are built to a fixed capacity, you build much smaller units. You standardize those units, and then you build your capacity by taking those units like Lego blocks and putting them next to each other to build up your capacity. And this is the idea of numbering up rather than scaling up, because it gives you flexibility that you don't get by designing and building a full-scale plant. It allows you to achieve certain economies of scale by using multiples of the same equipment and parts, and it can significantly reduce upfront costs and capital expenditure. What it does primarily, though, is it gives you the flexibility to adjust to changes in demand for your product. So like I mentioned in the downturn of 2008, or what we have right now, some of the modular production units can be taken offline to reduce the capacity, or they could even be packed up and moved to other locations where they're maybe more needed. When demand rises, you could do the opposite and then rebuild your capacity. It's an excellent concept. It's not that easy to implement. That's why it's taken so long, but we're working on it. I want to give an example. Here in Germany, there's a company, a chemical company, Evonik, and Evonik has recognized that that this is going to be a big thing for the process industry. So they've gotten actively involved with some of the suppliers, including Phoenix Contact and ThinkWorks is from PDC, that software. Just last year, the company applied this MTP concept to a plant in Singapore for the first time. And now this year, they've been working on installations of pilot plants in Germany. Apparently, so far, they've recognized the potential, but they have not yet built a full-scale plant that's based purely on these modules. And in the photo below, you can see a photo of 3 modules put next to each other. I don't know exactly what they do. I can't recognize it. But if you look down, it looks like they're probably on wheels, or at least on skids, so they can be easily moved and easily reconfigured if need be. So what is modular type package exactly? Well, it's a response to the stiffness of the rigidness of full-scale plants with no flexibility for capacity, and the need for the need for flexibility for that capacity. In general, we feel that investments will have higher returns because equipment is simply used better. It's used more often. It's used more efficiently. The average lifespan of each unit will probably be higher because they're reusable. They don't have to be junked when if the plant is closed. And the nice thing is that our reusability supports the circular economy. For short-lived specialty chemicals, for example, you can produce smaller quantities. And in the interest of time, I'm going to skip over a couple of these things because I know I just have 1 or 2 more minutes to go. Let's take a look at what it takes. I think this is more important to emphasize. It takes a new mentality. It takes new approaches to engineering, and it takes standardization. I mentioned Namor is an organization of chemical companies, of end users, that is currently working on standardizing MTP. Rather than optimizing the process to achieve a capacity range, the plant uses standard existing and reusable modules to achieve the increases in capacity, as I talked about. I put together, I'm not a process engineer, so I put together examples. Feed preparation, PAT is an interesting thing that I've actually researched in the past. Separators, reactors, heat exchangers, or an assembly of pumps, valves with the measurement and the controls built right onto the same skid. Challenges are that, as I mentioned with the Evonik project, it's currently limited just to small scale stuff, so laboratory and pilot plants. As far as I know, no industrial scale modular plant has been built around MTP yet, but it's coming. The CapEx costs I mentioned at the beginning are definitely there, they're possible, but that there is some excess cost with modular units. You have additional piping, you have more instrumentation, you probably have more controllers out there because every unit has its own controller. The question of how large it should be is still open to debate. Should it be, it's not going to be the size, it's not going to be 100%, it's going to be smaller. Is it 10% smaller? 20, 30%, 50%. For the skip one point, there's also not yet any clear business models for the different partners that are involved, for engineering firms, for the equipment builders, and for the end users, the owner operators. And finally, owner operators need to realize economic returns at several levels, not just one at the plant, at the business unit, or the corporate level. So what we hear from Evonik is that the standard is not finished, but it's sufficiently advanced that you can use it. It's important to, if you're an end user considering this, to review your process engineering approaches and see if you have the tools and the mentality and the willingness in your people to make this shift. Most important is to become familiar with the standards, and if you want, you can also become active and you can join these organizations and you can share your voice. And finally, I like to recommend following developments of companies like ABB, Siemens, Vago, Phoenix Contact, and PTC are just about 5 or so companies that are actually involved in doing practical applications of MTP. So to really summarize very quickly, architectures are evolving. I mentioned that. I showed 2 models. Are we consolidating or are we distributing? The reality will be that we'll probably have both. We'll probably have virtualization will help consolidate things, but increased intelligence will lead to more distribution. 2 different types of companies are going to compete for this space, the IT companies and the OT companies. I think OT companies are going to win because these are the guys that have the domain expertise. I mentioned industrial 5G is going to accelerate this a lot starting in about 2 years from now. And again, the standard for MTP is not finished, but it's advanced enough that we can get going on it. And on that note, I want to end my presentation. And I'm going to...
Thanks, David, for an excellent presentation. Before